Kia ora tātou, welcome to this video where we will look at first ionisation energy. We'll introduce the concept and then we will look at the periodic trends in first ionisation energy. So if we take a lithium atom, just to explain the concept, there's 3 protons in the nucleus and then we've got 3 electrons in its shells. So the first ionisation energy would be the energy required to turn this into an ion. So to turn this into an ion, we would get rid of that electron. So this is the first part of it, is that to turn it into its first ion, we're getting rid of that 1 electron. And the first ionisation energy describes how much energy would be required to remove 1 electron from each lithium atom, if this is a lithium atom, in 1 mole of lithium atoms, and they have to be in their gaseous state. So we could show this as a chemical reaction. We could show, if we were using lithium as an example, it would be lithium gas, so 1 mole of lithium as a gas, and that would turn into a lithium cation because we've removed 1 electron plus the electron that we removed, and we would show the change in enthalpy. So the energy required to make this happen would be a certain amount, so it'd be a positive value because it's going to be absorbing energy, and then the units will be kilojoules per mole. So I have seen questions that have simply asked to write this equation, and if you did have to write the equation, you'll just do that part there because we haven't been given the change in enthalpy. We would have to be given that in the table. There's no way we can work it out. So if you have to write down the definition of the first ionisation energy, here is a definition for you. The ionisation energy is the energy needed to remove an electron from each atom in 1 mole of gaseous atoms. So the next part is that we need to again look at trends in the periodic table of the first ionisation energy. So if we've got the outer electrons that are held relatively tightly, then that's going to require more energy to remove those outer electrons. If we've got the outer electrons that are held loosely, then that's going to require less energy to remove those. So that is directly related to the atomic radius. So when we have a small atomic radius, that indicates that those electrons are held onto really tightly. And if we've got a large radius, that indicates that they're not held onto quite so tightly. The electrostatic attraction between the electrons in the nucleus is less. So as we're going, if we've got the periodic table, as we're going across the periodic table, we know that the atomic radius will decrease. So that means that the electrons are held more tightly. So the first ionisation energy will increase as we're going across the periods. When we go down the periodic table, we know that the atomic radius of atoms increase, and so that gives us the indication that the first ionisation energy will decrease, so because it's going to require less energy to remove those electrons. So let's have a look at how we would explain, if we needed to, the trends in the periodic table of the first ionisation energy. So if we were going down a group, what would happen? So yeah, let's say we've got lithium and sodium. So lithium's got 3 protons and 2 outer shells. I'll do another. So that's the nucleus, and then sodium's got 11 protons and 1, 2, 3 outer shells with 1 electron for both of them in their final shell. So the things that we looked at when we were talking about atomic radius was that first of all, there's a greater number of protons as we go down a group. However, so this will increase the nuclear charge. We need to write that as well. Increase the nuclear charge. However, as we're going down, the outer electrons are being added further away from the nucleus. So the higher energy levels, higher energy levels are further away. And the other thing is that there are more energy levels in between. So sodium's got 1, 2 energy levels in between the nucleus and the outer electron, whereas lithium has only got 1. So there is an increased amount of shielding from the inner shells. So we would say, therefore, there is a decrease in electrostatic attraction for the outer electrons, or valence electron. So, because that electrostatic attraction is decreasing, the first ionization energy will decrease. So that's how we would explain the first ionization energy going down a group. How would we do it if we're talking about going across a period? So that's seems to be my favorite, that we'll use lithium again, and then we'll go across to fluorine. So lithium has got 3 protons and 2 electron shells, and fluorine has got 9 protons and 2 electron shells. Let's do the third circle there to show the nucleus. So in this case, we are, as we're going across the period, we need to say that we're increasing the number of protons. However, these and the electrons are being added to the same energy level. So this means that the electrostatic attraction increases, so we're going to have a greater first ionization energy. As we go across the period. So just one thing to add here, sorry, we increase the number of electrons, therefore we've increased the nuclear charge. So hopefully we're starting to see some patterns emerging. So we always kind of, for atomic radius and for our first ionization energy, we're giving our explanations and leading up to whether or not we've increased or decreased the electrostatic attraction between the nucleus and the electrons, and then we say whether or not that increased electrostatic attraction has what effect that's had on either the atomic radius or the ionization energy. Yeah, and that's it. So next we're going to look into trends in electronegativity, and it's all very related. It's all just about learning how to construct that exam answer. Thanks for watching. See you all next time.